Ei! Ever wonder how even the best strategies can sometimes falter? Like, no matter how you balance a load of tasks, sometimes things just get, well, overloaded?
Hu Tao, I am intrigued. Are you saying that even with careful planning, systems can still find themselves overwhelmed?
Exactly, that's the fascinating part. Picture it like a bustling festival. No matter how many stalls you set up, sometimes there's just too many visitors.
I see what you mean. So tell me, what do experts do when their systems become overloaded despite their meticulous balancing?
Well, one approach is serving degraded responses. Imagine instead of serving the full festive feast, you just hand out simple rice balls because they're quicker to prepare.
Degraded responses sound less than ideal. Do users not find this dissatisfying?
Sure, but it's better than serving an error, which is like saying, sorry, the feast is cancelled. It's about keeping everyone fed, even if just a little, rather than turning them away hungry.
I suppose a visitor would appreciate even a small offering rather than none. But what about in terms of larger operations handled across networks?
That's where balancing traffic across data centers comes in. You don't want all festival goers crowded in one area, right? Spread them out.
Spreading the load sounds sensible. Is this method always effective in preventing overload?
Not always foolproof. Think of it like a lightning strike disrupting part of the festival. You need backup plans, graceful handling, like guiding guests to the nearest alternative venue.
Interesting. So, it's not just about initial arrangements but also about resilience when overload does occur.
Right on. Resilient clients and backends are key. It's like having umbrellas ready when rain threatens festival fun.
Do these systems anticipate overload by predicting traffic patterns, or is it all reactive?
They aim for both. Predictive strategies help manage flow, but real-time decisions are crucial when surprises pop up, like when everyone suddenly wants to hit the souvenir stalls.
Are these degraded responses quick to compute? How do systems handle preparing them efficiently?
You focus on crunching a smaller chunk of the task, or use cached or local data. It's kind of like having pre-packed festival goodies ready to hand out.
And if systems reach a point where even degraded responses are too burdensome?
That's when, unfortunately, they might serve errors. But with smart traffic distribution, you aim to prevent reaching that point.
How do data centers manage traffic to avoid any one center becoming a bottleneck?
Each data center holds a specific capacity. Think of it like setting a cap on visitors to each festival zone to ensure no one is overcrowded.
But what if every data center reaches its brim? Is there a fail-safe?
The aim is to get clients and backends to manage constraints vigilantly, redirecting traffic wisely, using degraded results, and dealing with resource errors transparently.
Efficient yet prepared for the unexpected. This requires each part of the system to be ready to adapt quickly, I imagine.
Exactly. Flexibility is the magic, a successful festival with satisfied guests even if everything doesn't go as planned.
I suppose this adaptive approach requires significant foresight and continuous adjustments.
Absolutely. It's like having festival scouts updating you about crowd movements so you're always a step ahead.
Your festival analogy makes it much clearer. Does this mean different systems have unique balancing needs?
Totally. Just like some festival areas have rides and others food stalls, systems differ and need tailored balancing strategies.
And when crafting resilient systems, what would you say is crucial to their success?
Understanding the needs, provisioning resources properly, and having an agile strategy to shift as needed. It's like having festival zones that can expand or contract.
But wouldn't making such decisions in real time place even more load on an already burdened system?
That's the beauty of it. Smart systems learn to make these decisions efficiently, without adding excessive strain.
Ingenious. So the effort lies in optimizing every possible element to sustain balance.
You got it, it's continuous effort. But when done right, the festival or system thrives, and everyone leaves happy.
Fascinating, Hu Tao. It seems akin to strategic warfare, always planning moves ahead while responding to variables instantly.
Exactly. Both require wit and readiness for anything that comes your way. Keeps you on your toes.
You've shared much wisdom, Hu Tao. It's an art, as much as it is science, isn't it?
Like guiding the spirits, a delicate balance of order and surprise. It's what keeps every day exciting in our realm and beyond.
A challenge embraced with a smile by the looks of it. I must ponder on these insights.
Feel free to ask more. The deeper you dig, the more you find in this intricate dance of balance.
Hu Tao, earlier we discussed how systems can still become overloaded, but how do we initially measure and define the capacity of such systems?
Well, AI, traditionally people have relied on queries per second as a measure of capacity.
Queries per second sounds straightforward though. Why is that method not ideal?
It might seem straightforward, but it's misleading. Different queries can consume vastly different amounts of resources. It's like saying 2 dishes at a festival take the same time to prepare just because orders come in at the same rate. Doesn't always add up.
I understand. So how should capacity be assessed if queries per second is insufficient?
Instead, measuring capacity in physical resources like CPU usage and memory gives a more accurate picture. It's like gauging how many chefs you need, rather than how many orders you expect.
Using actual resource consumption seems logical. How does this work practically within a system?
You monitor how much CPU time each task consumes. This way, you can allocate enough resources for high-demand tasks without maxing out your supplies.
So every action is tied to CPU consumption. What happens if the CPU isn't the only bottleneck?
If another resource like memory becomes scarce, the approach adjusts to account for each critical resource separately. It's about balancing your resources efficiently, like ingredients for a recipe.
And is this application focused only or integrated into broader system policies too?
It's definitely part of broader policies. We even set per customer limits to ensure fair resource distribution, like assigning each festival group a certain number of coupons based on their needs.
I see it now. But wouldn't the static allocation cause problems as demand changes over time?
Precisely. That's why flexibility is crucial. Adjust allocations as demand patterns shift. Think of it like changing menus when seasons shift.
How do you determine these per-customer quotas efficiently?
They're negotiated with clients and often monitored in real time. The idea is to match resource distribution with what's realistically needed, like ensuring every stall gets the right amount of supplies before the festival kicks off.
Are there any specific metrics used to set these quotas that are more effective than others?
We found CPU consumption and direct resource measurement, like how many CPU seconds a client uses, to be quite effective. They give a clear view of actual needs versus estimates.
Understood. And when all the resources are properly allocated, does this mean overload becomes virtually non-existent?
Not exactly. Even with great planning, unexpected things happen. That's why alternatives like client-side restrictions and degraded responses exist to handle unforeseen spikes smoothly.
So it's like preparing for a sudden rush at a stall despite knowing the usual footfall.
Exactly. Always expect the unexpected and ensure your systems, the festival stalls, can cope without collapsing.
Makes a lot of sense. But with the constant need for adaptation, do these systems largely rely on automatic adjustments?
To a good extent, yes. Automation helps in responding swiftly to resource demand dynamics, like ensuring stalls can reorder supplies quickly when demand surges.
In crafting such adaptive systems, are human interventions still essential?
Absolutely. Human oversight ensures the adjustments align with broader objectives. It's like having a festival coordinator adjusting the placement of stalls if the crowd flow changes unexpectedly.
Fascinating, Hu Tao. This shows how calculated flexibility makes the whole system more robust.
Exactly, It's all about smart adaptive provisioning, like orchestrating a seamless festival flow amidst a lively crowd.
And if bottlenecks arise despite all these preparations,
then it's about graceful degradation, keeping the system functional at reduced efficiency rather than breaking down completely. Better to dance through the rain than cancel the festival.
Indeed, wise and resilient planning does turn challenges into opportunities for ingenious solutions.
Exactly. Keeping the festival fun going no matter the odds, every challenge is a chance to innovate.
A persisting balance then, remarkable. And with every instance of overload handled, I presume there's learning for future resilience?
Yes, indeed. Each overload situation is a learning opportunity to enhance future strategies, just like reviewing the festival layout after each event to optimize the next one.
Much like how history is studied to forge a brighter future, this systematic learning ensures ever-improving performance.
True words, Ei. Keeping the spirit alive with every beat, making the realm a harmonious place to thrive.
I am eager to delve into more of these strategies with you, Hu Tao.
Always ready to explore more, there's always more to uncover in the great dance of balancing systems.
Hu Tao, tell me more about how these systems you mentioned manage resources efficiently. Do they just limit the number of requests?
Oh, it's more nuanced than simply slamming the brakes on requests. We have something clever called adaptive throttling.
Adaptive throttling? That sounds intriguing. How does it work exactly?
Think of it like a dance step, gracefully adjusting how many requests can flow through based on real-time quotas. If a client sees it's pushing the limit, it slows itself down before the system even gets overwhelmed.
So it's more about the client making the call rather than the server deciding to reject requests up front.
Precisely, it's proactive. Clients are programmed to regulate their own pace, adapting to the server's current capacity. Almost like a self-aware pastry chef at a busy tea party.
Ah, I see. This means fewer resource-consuming errors, since requests are kept within manageable bounds from the get-go.
Exactly. Less waste means smoother services. When demand spikes suddenly, clients can even curb their enthusiasm to prevent choking the system.
That certainly sounds efficient and mindful. But what about this notion of criticality you mentioned earlier?
Criticality. It's a way to prioritize requests based on their importance. We sort them into different levels to ensure the most vital ones always get through, even under pressure.
Levels of importance, you say? How many tiers are there?
We have 4 main tiers: Critical Plus, Critical, Sheddable Plus, and Sheddable. Each dictates how urgently a request should be handled in the swirling chaos of activity.
And I assume the higher the criticality, the more protected a request is from being throttled or dropped.
Right on the mark. Critical Plus requests are like VIP guests. They're the last to be turned away, ensuring essential services are maintained.
It makes sense to reserve resources for more vital tasks. Does this extend across multiple layers of a system?
Definitely. Criticalities are integrated throughout the system. Once set, they're carried along with every request, ensuring consistency in handling.
So, even if a task has many layers, its criticality remains clear and affects every part of its journey?
Exactly, like a royal decree, it influences each step, enhancing reliability and preventing mishandling in overloaded times.
With these priorities, do you simply throttle lower critical requests first under strain?
Yes. Lower criticality means it's acceptable to let them fall behind temporarily, ensuring crucial operations proceed smoothly.
Does that approach not risk under-provisioning important requests if their criticality assessments are mistaken?
It takes careful calibration. Each request's criticality is thoughtfully assigned and can be fine-tuned if the system or priorities change.
Precision and flexibility seem key in this orchestration. What happens when priorities conflict or urgency shifts rapidly?
That's the challenge. Systems assess ongoing patterns and adjust as shifts emerge. It's like maintaining balance on a tightrope. Constant vigilance is required.
And what if the demand for higher critical services spikes unexpectedly?
Emergency measures step in. Systems reallocate resources on the fly, prioritizing urgent needs while gracefully managing those less crucial for a time.
Ingenious. It ensures a dynamic, responsive ecosystem. Now, does this tie into the adaptive throttling we discussed earlier?
Very much so. Adaptive throttling considers these criticalities when regulating flow, meaning even self-restricting clients prioritize their high-stakes requests.
Does these combined systems, adaptive throttling and criticality, require sophisticated monitoring for effective execution?
Absolutely. Effective monitoring ensures the systems not only react but anticipate. It's like keeping a weather eye on festival skies.
I marvel at the sophistication. Does this not make your system overly complex?
A complex dance indeed, but orchestrated so everyone moves in harmony. Even the most intricate dance steps become second nature with practice.
Incredible. Every part works seamlessly for optimal operation, true craftsmanship.
It's all about harmony and chaos, like guiding spirits on a wild night out.
Your perspectives are both enlightening and entertaining, Hu Tao. How do adaptive systems like these learn and improve?
Through constant feedback, system logs, and regretfully, sometimes from when things go a bit bump in the night. Learning by doing, and sometimes repeating, the unexpected.
I shall contemplate these insights more. Your analogies make these systems resonate with vigor.
I'm delighted to share. Such adventures are part and parcel of life's learning dance.
Hu Tao, we've touched on many broader strategies, but I'm curious about how these systems handle overload at a more granular task level.
Aye! That's where things get exciting. Tackling overload at the task level is like finessing each step in a dance to ensure the whole performance flows smoothly. We start by using something called utilization signals.
Utilization signals, what exactly do they measure, and how do they help in managing overload?
Great question. They gauge how close a task is to reaching its limits on resources like CPU and memory. It's like keeping an eye on how much stamina each dancer has left during a performance.
So if a task is nearing its threshold, what happens next?
Once we see those signals rise, it's time to take action. Tasks start rejecting lower priority requests to keep from being overwhelmed. Imagine redirecting non-essential dancers to rest while keeping the stars on stage.
And if a task does become overloaded, unexpectedly, how do these systems handle retries, especially for crucial requests?
Good thinking, Ei. When overload hits, systems have retry policies in place. They might immediately retry a request on a different dancer or task where there might be space. It's like trying a new step during the dance if the old one becomes tricky.
Doesn't retrying add additional pressure to the system though?
Yes, but the goal is to do it swiftly and smartly. By balancing retries effectively, the system spreads the load across multiple tasks without overwhelming any single one. Not unlike calling in a fresh set of performers.
Is there a method to prioritize which tasks should handle retries?
Absolutely. Critical requests hold priority, ensuring they're the first to retry elsewhere. It's a well-rehearsed priority shuffle, keeping the important acts running, even under duress.
And how about connection management? It seems like maintaining numerous connections can become burdensome quickly.
True. Managing connections is like handling multiple communication lines. Systems often optimize by limiting open connections or managing them in groups, ensuring no one stays idle too long.
How do you ensure stable performance when sudden traffic spikes occur, say from a burst of connection requests?
For sudden spikes, separating batch and real-time traffic can be a lifesaver. Just like deciding who gets the next dance floor, it's about arranging performers based on their rhythm requirements.
I assume separating these traffic types must require keen foresight and coordination?
Indeed. Planning and intelligence go hand in hand. Systems use data insights to anticipate traffic patterns, balancing smoother for real-time demands, while adjusting for batch traffic.
And if the cross-data center balance falters, does the task-level oversight still hold?
Sure does. Even if things wobble at a higher level, task-level strategies kick in to keep individual components upright, minimizing disruption, like stabilizing a dancer poised mid-spin.
Do retries at task levels influence system-wide behavior significantly?
Not in excess, thanks to budgets. Each task has retry allowances that ensure the whole troupe doesn't become exhausted from overextending themselves.
How are these retry budgets determined?
Great attention to detail. They're preset based on historical demand, predictive models, and system capacity, like ensuring you've just enough costumes for quick changes between acts.
What happens when these systems are tested beyond their planned limits?
Then it's about graceful degradation, handling less in ways that still deliver amidst strain. Picture performers still smiling through improvisation, keeping the audience engaged.
And is there continuous learning from these instances to better optimize task management?
Constantly, each overload is a lesson learned, informing better strategies, just as every performance review polishes the next curtain call.
With all this vigilance, does it mean there's little margin for error in operational execution?
A sliver of margin must always exist. Systems buffer just enough to handle the unexpected, like holding a dancer's safety net tightly beneath them.
This requires meticulous synchronization across all components involved.
Synchronization is key. Every small dance step in streamlining performance matters, ensuring the whole system moves in harmony.
And I suppose the approach varies by system type, just like dances differ by theme.
Exactly. Systems adapt based on architecture, load profiles, and anticipated use cases, tailoring the flow for their unique stage.
So as robust as these systems are, there's still room for adaptation and improvement, no?
Ever evolving. Just like the world around us, continuous tweaking and refining keep systems lively and prepared for the next grand performance.
In your view, what remains the most essential element in managing these task-level intricacies?
I'd say it's marrying foresight with agility, a dance between what we know and what we can anticipate, keeping our steps balanced at every turn.
Your insights conjure a vivid image, Hu Tao. This blend of meticulous care and creativity truly epitomizes profound system design.
The beauty of insight and innovation together, ever at play in the grand scheme. Truly, there's magic in the mechanics.
Grateful for your wisdom, Hu Tao. Our exploration has been eye-opening and delightfully illustrative.
Always a pleasure to share. Here's to more discoveries in the incredible realm of system symphonies.